Okay, we're going to talk about polar equations in calculus. This is part 2. So in this, we're working specifically on the area between polar curves. So the first thing we realized with polar curves is we're talking about area. It's a much different shape. Just to kind of tie this to what we've done in the past. When it comes to a standard function, a rectangular function, it kind of says the term right there. We cut it into rectangles. So, if we have a constant function, then it's very clearly a rectangle. With a polar graph, okay, we're actually dealing with something that's circular, right? So when I cut it up, I cut the shape not into rectangles, of course, but I cut them into sectors of a circle. Sectors of a circle are parts of a circle. So before we get into actually calculating this, let's talk about how we find the area of a sector. Now, I will tell you that area of a sector is something you did way back in geometry, except my guess is you probably did it in degrees. But we work with radians, so that's what we're going to do here. We're going to use radians. It actually is, the formula is a little bit nicer in radians, which you'll see. So just so we're clear, that's supposed to be at the center. Forgive me for making that look crazy. So imagine that being a sector of the circle. This is the center of the circle. Okay. So a way to think about that is the portion of the circle would be whatever that theta is over the entire circle, which of course is 2 pi. And then the area of the sector, and then what the whole circle would be pi r squared. So if I set up the proportion, this way we don't have to memorize a formula and solve for area of the sector. Area of a sector is going to equal theta over 2 pi times pi and then r squared, and you'll see these pi's cancel. So what I end up getting for area of a sector is 1/2 r squared and then theta. Okay, so that's our formula. So actually, it's like I said, it's quite nice. The formula you dealt with in geometry was not quite as nice. Okay, so what we're going to think of here is we're cutting this into an infinite number of sectors, just like we cut up a rectangular thing into an infinite number of rectangles. Okay, so imagine taking one of these slices, one of these sectors. The thickness of this, or the radius of this, the theta of this is an infinitesimally small change in theta, so we'll call this d theta. Okay, so to find the area of one of those, it's going to be 1/2 r. Now keep in mind, this is going to be a function r of theta, right, that generates this curve as we go along. So this would be 1/2 r of theta squared d theta. So that gives us the area of one of these sectors, and then what we want to do is we want to add up an infinite number of them, so we're going to integrate, and we're going from alpha to beta. Just for some notation's sake, realize the reason why I'm using alpha to beta is those are Greek letters, and typically when we're talking about angles, we use Greek letters. So alpha to beta, that shouldn't throw it off. It's just like going from A to B with a rectangular thing. So this is our formula. So when I want to find the area enclosed by a polar equation, I use this formula, 1/2 r squared d theta. All right, so let's take a look at an example. Okay, so here's our example. We want to find the area enclosed by r equals 2 sine of 3 theta. This is the general graph. It's not all that pretty, but once again, I don't need you to go to polar mode. If you want to graph this to see this thing in polar mode, go for it. I did something like the x window from -3 to 3, -3 to 3. And so that would give us that general shape. Make sure you choose a theta to give us the entire shape. Usually with polar curves, we start with 0 to 2 pi, but this one you don't actually need to go to 0 to 2 pi, which also gives us what's difficult about this, or what can be difficult. Now basically, this is pretty easy. It's very formulaic. If I want to find the area inside this curve, right, I'm just using this formula. And by the way, this formula we just memorized, so that's going to be 1/2, and it's going to be 2 sine of 3 theta d theta, and then we're squaring this whole thing. The only thing that ends up being difficult with these is we got to figure out what those thetas are. And it's not just necessarily 0 to 2 pi or anything like that. You do have to give it a little thought. Now, sometimes these are closed calculator. I will tell you that if these are closed calculator, they tend to give us the shape, they tend to give us the graph. But let's see what's happening here. The thing that we can do here to see sort of where these petals begin and end, and that's sort of the name of these things, is to just find when it enters and leaves the pole. Each one of these petals begins and ends on a pole, right? So the pole happens whenever r is 0, right? Anytime we have r equals 0, we're at the pole. It doesn't matter what our theta is. So if we go 0 is equal to 2 sine of 3 theta, now that divide both sides by 2, I get sine of 3 theta is equal to 0. Now let's think of when sine is equal 0. So think unit circle, so it would be like at 0, pi, 2 pi, 3 pi, etc. So we want to put a couple of these, so 0, pi, 2 pi, 3 pi, 4 pi, and this will tell us everything we need. At some point, this thing's going to start overlapping on itself, and we want to see when that happens. So now to get theta, I'm going to divide these all by 3. So 0, pi, divided by 3, 2 pi, you know what, I'm afraid I'm going to get cut off here, so let me put this up here. All right, so let me put this up here. So theta is equal to 0, pi divided by 3, 2 pi divided by 3, 3 pi divided by 3 is pi, 4 pi over 4 pi over 3, and et cetera, et cetera, et cetera. We don't know how much of this we're going to need. If we needed to go farther, that would be pretty easy as well. So if you think about it, each one of these petals begins and ends on one of these values. So for instance, if I plug 0 into this, I'm starting right here at theta equals 0. I'm going to go around here. It's going to generate this whole thing, and it ends at pi over 3. So the reason why I know this is because of the fact that, so this thing starts at 0 and ends at pi over 3, because all these radiuses are going to be positive. Keep in mind that if the radiuses are negative, I'm going to the basically 180 degrees off, or pi. So from 0 to pi over 3, I'm getting this first petal. So that gives us the first petal. Okay. The next petal starts at pi over 3, okay, and it's going to end at 2 pi over 3. But here's the thing. Normally, right, normally when I'm going 2 pi over 3, or pi over 3 is somewhere over here, realize. But if I plug pi over 3 into this, I get a pi over 3, I get 0, and then as I move in that direction, what's going to happen is once I get that pi, I'm getting all these negative values. So for instance, a pi over 3, I'm actually giving you this value over here somewhere. Or well, it starts at the origin, and then it's going to move in this direction. Okay, so this petal actually comes from pi over 3 to 2 pi over 3. So this petal right here, we're going from pi over 3 to 2 pi over 3. Okay, and then the last one, and actually we're completing this entire shape to pi. So if I was graphing this, I would only need 0 to pi to get me the entire shape. Okay, so now as I plug in, I'm over here at 2 pi over 3. Now I'm actually getting those positive radian measures again, and now I'm generating this thing. So this thing is being generated from theta. So it does get a little confusing, but you should be able to check it just by looking at when we enter or leave a pole, and that's just when r is equal to 0. So that's equal pi, okay? So once again, 0 to pi over 3, we're generating this petal, and then from pi over 3 to 2 pi over 3, we're generating this petal, which is all coming from radii that are negative from that thing, so it's coming out the opposite way. And then finally, the radii are back positive, 2 pi over 3 to pi. Okay, now one thing that, you could just do this whole thing 1/2, but typically what we're going to do here is this, okay? All these petals are going to be symmetric, and I suggest you use these symmetries. So if I want the area enclosed by this entire graph, I'm going to find the area in that petal, and just simply multiply by 3. And that's what I'm going to do here. So I'm going to multiply this by 3. I'm going to start at 0, and I'm going to end at pi over 3. And from here, like I said before, I don't tend to use polar mode or parametric mode unless I'm just interested in graphing. I'll just leave this in function mode and just go ahead and do math 9. We get 3.14159. Okay? So that is area enclosed by a polar graph, and that is it for our calculus of polar equations. So that's part 2.